Alright, so we saw the setup on the oscilloscope with the parallel AC-RC circuit, and I started to do some scratchings on this paper before. I've added a little bit to it since, so let's work our way through it. We did take some measurements before. We took a measurement not across this resistor, not across that capacitor, but if you recall what was in the circuit, we've got current flowing backwards and forwards at the 900 Hertz rate in this circuit, and therefore we've got one AC current path down through the resistor, and we've got one AC current path down effectively through the capacitor, because what's happening here, the capacitor is continually charging and discharging, and that's what's causing the AC current to be seen in that capacitive circuit there, that capacitive branch. So to measure these currents, I've had to put some small value resistors in series, and I've chosen to use 15 ohms for each resistor, and we measured those voltages, if you recall, across those resistors. So these were the voltages measured across each resistor, and then using simply I equals V divided by R, I came down to measure or calculate 4.8 milliamps in the resistive branch and 2.9 milliamps in the capacitive branch. And if this was a DC circuit, of course, we could simply add these together algebraically and we would come up with the total current in the circuit. But here we cannot do that because things are happening at different points in time in the circuit. Remember, we saw the acronym ELI the ICE man, and I've circled ICE here because in a capacitive circuit the current is always going effectively through the capacitor, is always going to be leading the voltage across the capacitor by 90 degrees. So if we look at the, well, let's first of all have a look at this phasor or vector diagram here, and the reference in this circuit has to be voltage because each component in the circuit shares the same voltage. So the voltage across the resistor, the voltage across the capacitor, and the voltage across the supply are all in parallel, hence they all lay on this reference phasor. The current going through the resistor, because it's not a reactive component, is not at all out of phase with the voltage, hence it goes on the reference phasor as well. But the current in the circuit has to be leading that voltage by 90 degrees. So here's our 2.9 milliamps, which is the circuit current here. Here's the 4.8 milliamps, which is the resistor current here. I've plotted them to scale, and then as we would with a tip to end phasor addition, I've drawn a parallelogram here, I've drawn in the resultant, and then we can do some maths on that resultant. Maybe if we like to go ahead and use the rectangular to polar function on the calculator would be the quickest way. So on my calculator that'd be pole 4.8, and it's in milliamps, they're both in milliamps, so I'll just go 4.8, 2.9, and enter. So let's go ahead and do that. That'll be shift pole 4.8. On this particular calculator it's comma and then 2.9. You see what I mean? They're both in milliamps, so there's no need to use exponents here. Equals, and on the FX82 with this 3-line display, beautiful, we get the resultant, which is going to actually be the total current flowing in the circuit. So we can label this now IT 5.6, I'll round that up, it's 5.61 milliamps, and the phase angle in the circuit, theta, and the phase angle represents, you might recall, what the leading current, what the current in the circuit and the supply voltage are apart from each other. So in this case, here's our supply voltage, and here's our current, so therefore the phase angle has to be here, theta, and that equals 31.14 degrees. 31.1 degrees, something like that. Here in colour, I've drawn what we actually saw on the oscilloscope screen, and that is that we had the capacitive current, because don't forget, these represent currents. Of course, the oscilloscope can only show voltage, so we had to make an effective current measuring device, and we did that with a bit of knowledge about Ohm's law. We put in some simple resistances there, and that voltage drop converts directly into a current. So this one here is actually in the blue, represents IC, that would be the 2.9 milliamps, and in the orange here would have been IR. And of course IR was 4.8 milliamps, so I haven't quite drawn those to scale. He was bigger than IC. And of course you can see that proportionally here, the voltage developed across our little 15 ohm sensing resistor. I'll put here R sense, and that's what these are commonly called, or current sense, R sense. So we got 72.1 millivolts developed across the resistive leg of the circuit, and we got 43.6 millivolts developed across the capacitive leg. So therefore the capacitor current is of course lower, and we calculated that down to 2.9 milliamps using I equals V on R. So I think that pretty well sums that up. Our phasor diagram giving us our resultant, and I did it using the polar function on the calculator. Of course, it could have also been done. IT would be equal to the square root of, and this is going to be the same deal, 4.8 squared plus 2.9 squared. And to save me doing that on the calculator, to get that resultant, which is the hypotenuse in this triangle, much easier to use rectangular, the polar translation function on the calculator, as I've done in previous videos. So that's pretty well it for part 2 of this, and then I think in part 3 we might come back and do an analysis on the impedance of the parallel circuit.